Hi everyone. Sorry that I missed explaining this in class today. I really made finding the nonlinear fit that's in a logarithmic um, function more difficult than it needed to be. So if we plot data and we see that it has again a logarithmic growth curve, so something that's a little bit flatter than a linear growth curve. In order to linearize the data and to be able to assess the residuals and confirm goodness of fit, the transformation that we're going to do on the data is not going to be on the y variable, but instead it's going to be on the x variable. And it's as simple as changing our x variable to ln of x. This is also why when they transform the data for this particular function, they set 1900 equal to 1. So that it would be well defined. Of course, if we take the logarithm of 0, it's undefined. So we can take the logarithm of 1, and that'll be our 0 value once we transform it. And our dependent variable, our y variable, is going to stay the same. So it's just going to be life expectancy. And it's just going to be equal to our values from up there. Copy down. So if I look at the scatter plot for this data, where I've done the natural logarithm on the x variable, and I look at the scatter plot, we can see that it's much more linear, that the data has been linearized. And so this is ln of x versus life expectancy. And if we find the linear regression line for the data, we can see it's 13.78x plus 42.698. And that is the same equation, or the same coefficients that we see up above, substituted for the original data, just substituting x with ln of x. And I apologize if I made that seem really complicated in class today. It's one of the simplest transformations that we can do. So to linearize data that has a logarithmic shape, we take the log of the x variable. And recall, to linearize data that had an exponential shape, we took the logarithm of the y variable. To linearize data that had a logistic shape, we ended up having to take ln of the y value over our carrying capacity minus our y variable.